Okay, we're all set.
Okay. Okay. Hi, everybody. So this is, let's see, session 3 of our modeling tutorial. And today what I'm going to talk about is computing static Green's functions, which is the sort of thing you would need if you're going to perform an inversion. So the topics that we'll be covering, or the concepts that we'll be covering in this session today, are first of all the generation of Green's functions in both 2D and 3D, and then also a specific type of output that Pilot can do is interpolated output at a specified set of points, and this is the output solution points option for Pilot. So that allows you to give, for example, a set of points that could correspond to GPS observation points, and to compute the solution interpolated to those points. We're also going to cover a bit of post-processing of HCF5 output using the Python package h5py. And that's, we'll do this for the 2D example when we're looking at the computed solution and trying to do our inversion. And we'll also be doing a simple, very simple linear inversion using NumPy. And then finally, we're going to plot up the inversion results using the matplotlib Python package. So what we do with Green's functions is we compute the deformation at either a point or set of points or over any part of the mesh we want due to unit slip at a fault vertex. And this is what you typically want for an inversion. And for Pilot, what we have, you apply slip at a vertex, and then it decreases linearly to 0 at the surrounding vertices. So this is somewhat similar to what you get when you have uniform slip on an Okada patch. But the difference is we have unit slip at the vertex, which decreases linearly. Or with Okada, you have uniform slip over a finite patch. So there is some slight difference in the way you interpret what the fault slip means. But you can get similar solutions using either method. And what this allows us to do using Pilot, we can compute the Green's functions using any arbitrarily complex elastic structure, which means we can have complicated material property variations, we can have the effects of topography, and any other types of effects that you wouldn't be able to represent with an elastic half-space solution. So we're going to cover 2 different examples today. The one that's a bit more in-depth is this first one, which we'll be covering first. It's the 2D example, which is in examples 2D Green's functions. And what we'll do, we'll go through the whole process. We'll compute fake observations using a simulated earthquake. That's step number 1. And we then compute those displacements, or compute displacements at the same observation sites using for our Green's functions. And then once we've generated the Green's functions, we'll invert these fake observations to get our inferred value of fault slip. And this is described in section 7.15 in the user manual. Then, just as a somewhat shorter example, one of our examples in 3D Hex 8 just shows the simple problem of how to calculate the Green's functions. And in that case, we're not going to perform an inversion. We're just going to show you how you generate the Green's functions, and possibly an interesting exercise for people might be to see if you could set up your own inversion using a problem like this. So the first one, the 2D Green's functions example, here's where the files are. You can follow along if you want, or you can do this later if you don't have enough time to follow. First of all, we'll generate the mesh using Qubit, but I'm not going to devote as much time to mesh generation today because we want to focus a little bit more on the generation of the Green's functions and then the post-processing that we're going to do. Then we're going to compute our synthetic observations for a fake earthquake, which we just do by running pilot using the eqsim.config file. And then we're going to generate the Green's functions that we can use in Inversion. And we'll do this by running pilot and changing the problem type from the normal time-dependent problem to pilot.problems.Green's functions. So this is a different type of problem that pilot can do. Then finally, well, actually not quite finally, first we'll invert for fault slip using a little Python script that we've written. That just does a simple linear inversion, which we'll talk about. And then finally, we'll visualize the inversion results using the matplotlib Python package. So the Python packages that we'll be using, first of all, there's NumPy, which gives you all sorts of abilities for scientific computing with Python. And it can do a lot of the same type of numerical functions that you can do in MATLAB. And NumPy is included in the pilot binary distribution. So this is one that you shouldn't have to install on your own. If you've set up Python to run, or pilot to run, then you should have NumPy available within your Python. The other one is the H5Py package, which allows us to access HDF5 files. And this is also included in the pilot binary distribution. And then the final package is matplotlib, which gives us 2D plotting for Python. And it's designed to be fairly similar to what you get in MATLAB. But now this one is not included in the pilot binary distribution, but you can get it from matplotlib.org. So once we've computed our fake data for the 2D example and we've generated our Green's functions, we're going to do an extremely simple linear inversion where we've created an augmented system of equations. This G is just your regular G matrix, which gives the response, which describes the coefficients. You multiply G times your, this M would be fault slip, and then you get your displacements on the ground surface. And we've augmented this by putting in a penalty parameter multiplied by this D matrix. And this multiplied by your augmented data, or by your fault slip, gives you your a priori model parameters. And so what you can do with this inversion, you can vary the penalty parameter, then it's multiplied by the D matrix. For the simple example we're doing, this D matrix is just the identity matrix. And our a priori data values or model parameter values are just 0. So this is what you call a minimum moment solution. So we can do that, and then once you have this augmented system of equations, you can form your generalized inverse, which you can find in most books, say like in Minky. And then you get your estimated model parameters by multiplying this your generalized inverse by your augmented data vector. And then we'll get to the, what's that? Go back?
Yeah. What does the superscript minus G stand for?
Oh, that means generalized inverse. That's just a kind of a notation that I know in particular Menke in his inverse theory book uses that type of notation to represent a generalized inverse, which means that it's not a true inverse, but you get the inverse solution to the problem in the least square sense using